Welcome to Green Chemistry. In this lesson, we will explore meta-analysis of reaction pathways using green retrosynthetic logic. We will connect chemistry with mathematics, statistics, and graphics to make the decisions crystal clear. Retrosynthesis means we start at the target molecule and think backward, breaking it into simpler precursors. The green logic adds sustainability metrics to each possible disconnection, so we can choose not only a feasible route, but a cleaner and safer one. We score routes with core green metrics. Atom economy is the mass of the desired product divided by the total mass of reactants times 100%. The E factor is the mass of waste divided by the mass of product. Process mass intensity is total mass divided by mass of product. We can also include energy intensity and hazard scores. Let us compare two illustrative pathways to the same target. Route A is 2 steps with yields of 80% and 90%. While Route B is 1 step at 70% yield. We also estimate waste and materials for each route to compute the green metrics. Suppose Route A uses 100 grams total inputs for 72 grams of product, so its process mass intensity is 100 over 72, about 1.39. Its E factor is 28 grams of waste over 72 grams of product, around 0.39. Atom economy is high at 85%. Route B uses 90 grams for 70 grams product, so the process mass intensity is 1.29, E factor is 20 grams over 70, about 0.29, but its atom economy is lower at 60% due to a sacrificial leaving group. Let us place these as badges under each panel. In a meta-analysis, we examine many reported routes. We can visualize the distribution of E factors and yields, compute means and confidence intervals, and compare families of chemistry like catalytic versus stoichiometric routes. We can formalize the mean and uncertainty. The weighted mean equals the sum of weights times observations divided by the sum of weights. The standard error of the mean equals standard deviation over square root of n, and a 95% interval is mean plus or minus 1.96 times the standard error. A Pareto plot helps us see trade-offs. Along the horizontal axis is E factor, lower is better. On the vertical axis is overall yield, higher is better. Points toward the upper left are most desirable. The connected line shows an approximate Pareto frontier of non-dominated routes. We can combine metrics into a single route score for quick ranking. For example, score equals plus W1 times atom economy, minus W2 times E factor, minus W3 times energy per kilogram, minus W4 times hazard, plus W5 times overall yield. We first normalize each metric so they are comparable, then choose weights that reflect the project goals. Retrosynthetic logic plus scoring suggests a path search problem. We propagate costs or scores along the tree and pick the route with the highest score. Here we illustrate costs accumulating from precursors up to the target, like dynamic programming. A visual mass balance reinforces atom economy. The incoming mass splits into product and waste. Thicker product flow means better atom economy and usually a lower E factor. Summary: 1. Retrosynthetic logic explores structure backwards. 2. Green metrics like atom economy, E factor, and process mass intensity quantify sustainability. 3. Meta-analysis aggregates many routes using statistical tools and Pareto graphics. For multi-criteria scoring and dynamic programming, help select the best pathway for greener chemistry. Green chemistry is better chemistry. Thank you for watching.